Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. Here we'll be looking at a question from the previous video, the one which was on trigonometry if it's a study of circles, where we made a slight case that trigonometry can be viewed as a study of circles, and we ended that with an integral application which involved a sector. If you remember, our sector looked something like this. The radius was 1, theta was equal to pi over 3, which is 60 degrees. We had something which looked like this, and we were extending a line down from here. This was 1 over 2 comma 0. This right here was my origin, 0 comma 0. This right here representing the radius, 1 comma 0. Over here we had 1 over 2 comma root 3 over 2, and this became over here 0 comma root 3 over 2 in terms of the y extension, or the y-axis extension of this. This entire figure here is my sector, and we were looking at the area of this portion between the triangle and between this border, the arc length. We're looking at this area over here. But what I want to look at in this is the total area of this sector. The total area of this shape was just basically the area of the sector. And how could we very easily do it? Just by using the formula for area of sector is half r squared theta, and we know it's half times r squared, which is just a 1, meaningless here, times pi over 3, and we get pi over 6. What we want to look at in this video is the determination of this area sector, the numerical determination of it using integral calculus. And that's why we're calling it a sector application. I know we're presenting videos here, these bunch of videos, or the ones previous to this, all before we even learned actual integration techniques, but that's fine, because once we learn those techniques in the very near future, you can always come back to these videos and do these on your own. But this way you have material, something to challenge yourself with, or something to motivate yourself with. You can look at this in terms of integral calculus in 3 ways, 2 of which are just an extension of the same way. In one way, you can look at everything in terms, and let's use proper terminology so we can learn to write these integral forms in proper terminology, and you can view this video as a way of learning how you can write these integral equations in proper form. You can look at everything here with regards to x. A of x, meaning you're looking at f of x in terms of equations presented in the y equals format. If you look at over here, you know, when you look at something in terms of a to the x, you're always looking at yt minus yb, top boundary curve and lower boundary curve with respect to dx. But if this is the entire shape, you don't really have a clear top boundary curve. You have a very clear bottom boundary curve, but you don't have a top boundary curve, because up to this point from 0 to half you have one top boundary curve, then from half to 1 you have another top boundary curve. So in this specific instance, you could look at everything as this. From interval along an x-axis dimension from 0 to half, we have a top boundary curve, which is this equation right over here of this line. You know, if you have 1 over 2 comma root 3 over 2 and 0 comma 0, you can easily use the slope and y equals mx plus b format and determine the equation of this line, and the equation of this line would be root 3x of this line over here. So from this interval to half, 0 to half, you have a top boundary curve of root 3x. The lower boundary curve is just this y equals 0 x-axis, which is just meaningless, and you don't have to even mention that. Plus, then from the interval of half up to this 1, you can look at this top boundary curve right here, which is a continuation of your unit circle. But this, you're examining a unit circle, only a portion of it. And this equation, as you saw in the previous example, was 1 minus x squared all root. And that's the top boundary curve over here. So it's 1 minus x squared. Lower boundary curve is just again x-axis. I won't even mention that, dx. That's one way of looking at it, and it won't be too bad to look at it in terms of this. Another way to look at it is in terms of area with respect to y, where now you're looking at right and left sides. If you look at this graph, you have a right side boundary curve, and you know, in these instances you look at something with a lower limit, upper limit, but along the y-axis, and then you're looking at right side curve, limiting curve, minus left side curve, limiting curve with respect to dy. And we do have a clear indication from 0 to 1, we have a clear right side curve, which is just 1 minus but y square root, because here you'd have to express the equation in the x equals format, right? That would be my right side curve. Sorry, but my left curve would be exactly this, what you see, but you'd have to express it in the x equals format, so x would equal to y over root 3 with respect to dy. But what would our intervals be from the lower extent of 0 to the upper extent of this root 3 over 2? See, root 3 over 2. Root 3 over 2. That's one way of looking at it. But you can also look at the same format here in a slightly more difficult manner, and you can break everything in intervals from 0 to half. I'm just talking about in terms of x-axis, from 0 to half, and then from half to 1, you can have a bunch of right side and left side curves. From 0 to half, you have this line here serving as a right boundary curve and this serving as a left boundary curve. But from half to 1, you have this side serving as a right boundary curve and then this line becoming a left boundary curve. Of course it's more complicated, but it is still another way. And again, you would still use vertical delimiting limits from 0 to root 3 over 2. You have this portion being examined where the right side is this imaginary x equals half line 1 over 2 minus this line over here, which would be have to express in x equals format, y over root 3 dy plus, you would add this part plus here. Remember, we're looking at the entire area of the sector. Then you look from, again, from 0 up to root 3 over 2. And from this portion right here to this portion, you have a right side which is this arc and the left side which is this x equals half. So here you would say 1 minus y square minus 1 over 2 with respect to dy, and this is yet another way. This entire way right over here is equal to just this over here. Why? Because think about it. Look, the intervals are all the same. You have a plus half over here and you'll end up having a minus half over here. These two portions will cancel out, so you'll end up with just this right over here and just this here. And look at the signs. Here this y over root 3 is attached to a minus, which it is, and here this integral of the root of 1 minus y squared is attached to a positive sign, and here it is. So you're seeing it exactly. This is an expanded form, this is the condensed form, and you can look at everything in terms of this equation right over here, or you can look at everything in terms of this equation right over here for this entire area of the sector. And if you did either method, you'd still end up with pi over 6 as your resulting answer for the area of the sector, and we would want to see that. And you could also show, if this entire sector were imagined to be a full circle, pi r square, having a radius of 1, the area of this entire circle would be a pi. Then you'd multiply by that factor theta over 2 pi, which I've talked about, and the factor over here is what? Pi times pi over 3 over 2 pi. Because we're looking at only a pi over 3 portion. See, the angle over here is just a pi over 3. This pi over 3 is a fraction of the full 2 pi. The full 2 pi. It's a fraction. So here's my factor. So pi times pi over 3 divided by 2 pi gives you what? It gives you pi square over 6 pi. And you simplify that, you get pi over 6 again. You see that. So what I want to do in this video is I want to look at this procedure right here. Area of this sector with regards to x dx. And area of the sector with regards to y dy, and you see the integral form here before you, and that's what we're going to run. Scenario number 1, scenario number 2, and in each instance we should get pi over 6, and that will be the gist of this video. Okay, let's look at the scenario number 1 where we integrate with respect to x and we do procedures with respect to dx. You know, from interval 0 to a half we have a top boundary, lower boundary. From half to 1 we have a top boundary, lower boundary. In each of these instances the lower boundary is just y equals 0, the x-axis, so you don't even have to bring them in. And you know how these equations have been derived. This right here is just an arc of an entire circle. X squared plus y squared equals r squared, where r is equal to 1. You solve for that y and you get this. And you know how this equation is derived. You have this origin point, you have this point right here. You do y equals mx plus b and you'll get this. Y is equal to root 3x, where the slope is root 3 positive and upward line, and there's no traditional y-intercept other than it being 0. Let's look here at the form. From 0 to half, the top boundary curve happens to be this root 3x. The lower boundary is y equals 0. We don't even have to bring it in, dx. Plus, here, from 1 over 2 up to 1, we have a top boundary curve right here. It's just 1 minus x squared with respect to dx. Here, this root 3 can be brought out as a coefficient, and let's do that. Once you learn the integral procedures, these integrations are not hard at all. Here, as you know now, is a trigonometric aspect or trigonometric function hidden in here. A is equal to 1, x is equal to sine theta, dx is equal to cosine theta d theta, and theta 1. Anytime you do a substitution, the intervals change. Theta 1, all of these values here equal the x in this equation, then you solve for theta. Half is equal to sine theta. Theta is equal to pi over 6, because half inverse sine is a pi over 6. Theta 2 is equal to pi over 2, especially when x is equal to 1. Let's do the integration of this. It's not hard. You have a root 3 sitting out. Once you learn the integral formulas, this becomes an x squared over 2. From an upper limit 1 over 2 to 0. Plus, remember all this you learn, and you can come back and review with what you see over here. When you do all of this, you've seen this enough times, you know what you're going to end up with. you have an interval here from pi over 6 to pi over 2, you'll end up eventually having cosine squared theta d theta. You've seen this too many times that we can just jump directly up to there. And when you see cosine squared theta, you always think about power reducing formula, and you write 1 plus cosine 2 theta over 2 d theta. We won't do anything with this right now. We'll put it on a hold. We'll only look over here. This 1 over 2 can come out, and you can split the integrals across the positive sign. You have pi over 6 pi over 2 d theta plus this plus is this plus right over here. 1 over 2 pi over 6 pi over 2 cosine 2 theta d theta. When you learn trigonometric substitution techniques, you see all of this by means of the polynomial substitution technique, a new set of substitutions which will affect the intervals. All of this will convert into this very good form, and I'll just write it out over here. It will convert into 1 over 4 from pi over 3 to pi. You'll have cosine u du. Why? Because we have a composite 2 theta. Multiplying pi over 6 by 2 gives you that. Multiplying pi over 2 by this 2, you get that. What you eventually end up seeing over here, and I'm going to just write it all out over here in a single format. As I've shown you, you have 1 over 4 here. You have a pi over 3 pi cosine u du. When you do, you still have to remember this. When you do the integral of this, what are you going to get? You'll get 1 over 2 theta pi over 2 to pi over 6 plus here you'll get sine u, which you will learn in the antiderivative of cosine u is the sine u, all over 4 from pi and pi over 3. So we have all our three things. Here's number 1, here's number 2, and here's number 3. We have to add them up. When you do this procedure right over here, you'll get root 3 over 2 times 1 over 2 squared, which is a 1 over 4. When you do this part right over here, you're putting a pi over 2 and a pi over 6. The difference of that is a pi over 3. Pi over 3 times 1 over 2, well, you get pi over 6 from right over here. When you look over here, you do sine of pi minus sine of 60. 0 minus root 3 over 2 will be minus root 3 over 2 over 4. You can verify all of this once you learn these techniques. When you combine all of this, what do you get? Root 3 over 8 over here plus pi over 6, and then you get minus root 3. Because this over 2 multiplies with this 4, you get root 3 over 8. You have a positive root 3 over 8 minus root 3 over 8, which cancel out, leaving you just pi over 6 as being the area of the sector. And we've already shown you that the area of the sector was pi over 6. We just had to show you using this procedure, which was the dx procedure. We'll call this dx because we're integrating with respect to dx. So based on this, we have a pi over 6, so we're good. We verified that. Now we want to look at the same question here, but using the dy procedure. We're able to integrate with respect to y dy, and I've shown you the template already at the beginning of this video, and then with that calculation and arrival at pi over 6 we'll end this video. So we are looking at the area of this sector having a radius of 1, and you know theta over here was equal to pi over 3 or 60 degrees, and the arc length is always determined as s is equal to r theta. S is equal to r theta. If r is 1 here, the arc length is equal to pi over 3, exactly what the angle is in terms of radians. And you know, when we're looking at this, as I showed you the template derivation of this, you could have looked at it from 0 to half in terms of just splitting this, and then from half to 1, but you ended up as xr, xl, then this was xr, then xl, but all of that still combined into this condensed form, and that condensed form is what we're looking at. We know over here with regards to y, equation must be in the x equals format when we're doing dy integration, and then you do right boundary curve, which is this portion or this arc of a complete circle, x squared plus y squared equals 1 for this unit circle having radius 1. You solve for that x and you get this. That's my right boundary curve. Left boundary curve is this line, y equals mx plus b form, which has equation y equals root 3x. You solve for x, you get y divided by root 3. So what is our entire procedure becomes? Area with respect to y, we're looking again from lower limit 0 to upper limit root 3 over 2 in terms of y dimension. XR, right boundary curve is this, root 1 minus y square, minus the left boundary curve, which is y divided by root 3, all with respect to dy. It's better if you just separate everything across this minus sign into individual integrals. 0 to root 3 over 2, root 1 minus y square dy, minus 0 to root 3 over 2 y dy. This over 1 over root 3, I'm bringing it right out here. Remember, at the end we should still get the area of the sector to be pi over 6, this entire area. pi over 6. Trigonometric values are present in here. If a is equal to 1, y is equal to sine theta, dy is equal to cosine theta, d theta. Theta 1 is equal to inverse sine of 0, which is 0. Theta 2 is equal to inverse sine of root 3 over 2, which is what? Pi over 3. By plugging in all of these substitutions, these items, we can re-characterize this entire aspect to 0 to pi over 3, and we end up having square root of cosine squared theta by means of substitution, isolation of 1, and the radical effect on this perfect square, which would end up in here, which would be cosine squared theta. That cosine squared theta will come out of the radical as a cosine theta, multiplying by dy, which was cosine theta, d theta. You combine all of this, what are you getting? You're getting cosine squared theta, d theta. Cosine squared theta, d theta. And when you learn trigonometric substitution techniques, you can do most of these steps in your head. Minus the integral of y will just be y squared over 2, which is what you have to learn in a very upcoming video. Times this 1 over root 3, which is sitting outside, affected by the interval root 3 over 2, 0. You know this opens up into 1 plus cosine 2 theta over 2 d theta, affected by the same interval 0 to pi over 3, which if you open it up, you can get 1 over 2, 0 pi over 3 d theta, plus 1 over 2, 0 pi over 3 cosine 2 theta d theta. This right here is easy, we can put it off aside. This right here is easy, we can put it off aside. We just have to look over here. By means of polynomial substitution, because we have a 2 theta, all of this, when you learn the technique, will become into 1 over 4 sine u from an upper limit 2 pi over 3 to 0. Why? Because this 2 will multiply with the 0 and give you a 0. 2 multiplied with pi over 3 give you 2 pi over 3. So let's incorporate all of these aspects we have into this equation, which we'll put right here on the bottom. We're going to have this coming out from right over here. Then we have all of this coming out from right over here. So let's add that over here. Here we ended up having 1 over 2 integral of d theta is just a theta from upper limit pi over 3 to 0. And then we had this part coming from this part. I remember all of this is coming from this, which is coming right here from that cosine squared theta. Because cosine squared theta by power reducing formula splits into two branches, which you see right over here. Here we had 1 over 4 sine u 2 pi over 3 to 0. So we have to compute this, this and this. And our result will be placed right over here. When you do this part over here, this is what's going to generate that pi over 6. You get 1 over 2 times pi over 3. That's from this first part. When you look over here, what's sine of 120? It's exactly the same of sine 60, because sine is positive in both the first and the second quadrant. You get 1 over 4 times root 3 over 2. Sine of 120 is the same thing as sine of 60, which is root 3 over 2, multiplying by this 1 over 4 sitting outside. Let's look right here. If you put root 3 over 2 into this square, you get 3 over 4. 3 over 4 divided by this 2 is a 3 over 8 multiplied by 1 over root 3. 1 over root 3 times 3 over 8. We just have to simplify all of this. 1 over 2 times pi over 3 is a pi over 6. Root 3 divided by 8, that's what I'm getting over here, plus root 3 over 8. I have a minus sign. Here I'm getting this radical root 3 affects this whole 3 to give you a root 3 on the top, and you have 8 here on the bottom. These cancel out and you end up having pi over 6 as the area, which is what we were looking for all along. And then you know now that the area of the sector being pi over 6, this entire sector right over here internally would have an area of pi over 6, and I've shown it to you. The very first way at the very introduction was just using the half r squared theta, or you can take a whole circle pi r squared and multiply by that factor, which converts a circle into a sector. Then we looked at it in terms of integration with respect to dx, and now we've looked at it in terms of integration with respect to dy, and we've seen all of this play through. And that was all I wanted to show you in this video. Yes, concepts which are a little advanced for those watching this video, because we haven't talked about integration techniques, but after you do understand those and learn those integration techniques, all of this, you can come back and revise. Thank you for watching. Have a nice day.